4 billion years ago, Earth was a toxic sphere of magma and volcanic ash. Today, it is wrapped in a dense, interconnected web of biology. This represents a massive shift in organizational complexity. Many assume life began in a single lucky moment, like the Frankenstein story, where a lightning bolt strikes a puddle of chemicals and jolts a cell into existence. Even Charles Darwin leaned into this idea of a localized starting point. He speculated on a warm little pond where proteins might form. He identified the need for a setting and ingredients, but the internal coordination required for a single cell was far beyond the chemistry of his era. The atoms required for life, carbon, hydrogen, oxygen, nitrogen, were already present on that early violent Earth. The challenge lies in explaining how these non-living ingredients reached a state of self-sustaining organization. Crossing this threshold required the early Earth to function as a planetary laboratory, bridging three technical requirements: a reliable power source, a method for storing information, and a physical boundary. First, a living system needs a continuous, stable flow of energy. Without it, the system slides toward equilibrium, a state where all chemical reactions stop and the structure decays. Deep-sea alkaline hydrothermal vents offer a geological setting that addresses this energy need through their porous mineral walls. These walls separate warm, alkaline fluid inside the vent from the acidic ancient ocean. This creates a proton gradient, a natural energy difference caused by a higher concentration of hydrogen ions. This setup functioned as a primitive metabolic engine. The geological pressure of that gradient drove early chemical reactions, forcing them to become more complex within the rock's pores. Life inherited this metabolic engine. The Earth's geology provided the initial energy supply, long before biology developed its own internal power systems. The next requirement is a system of memory. A living system must store its successful chemical arrangements and copy them for future use. Modern biology faces a circular dependency. DNA holds the instructions, but proteins are the molecular machines required to read and copy it. Neither can function without the other. The RNA world hypothesis suggests that RNA served as the bridge. RNA is a versatile molecule that can both carry genetic data and fold into complex shapes. Early RNA theoretically solved the paradox by acting as both the physical code and the chemical catalyst. It functioned as both the information hardware and the operational software, allowing chemistry to begin self-replicating. This dual capability provided a credible path between simple chemical building blocks and the arrival of Darwinian evolution. Even with power and code, molecules like RNA require a container. Without a physical boundary, they would dilute into the open ocean, making it impossible for them to interact. Volcanic hot springs provide a dynamic environment for this. Natural cycles of evaporation and flooding concentrate simple fatty acids along the edges of these pools. These concentrated fatty acids spontaneously assemble into protocells. These are primitive, spherical membranes that can trap RNA and other chemicals, creating a private internal environment. While we have successfully generated these individual chemical parts in laboratories, we still lack an explanation for their integration. The final challenge is proving how these separate components unified into a system that uses its own information to control its future state. Creating the parts is only the first step. Biology begins at the threshold where chemical reactions are replaced by historical, causal control. Life emerged through a planetary-scale collaboration. The atmosphere, oceans, and minerals work together to move energy through a massive chemical network. We often view matter as a passive, dead substrate, but these chemical steps suggest that matter, under specific physical laws and environmental constraints, is inherently capable of organizing into complex, cooperative systems. Whether life is rare or common, its emergence reveals a universe far more fertile than our theories once predicted. The chemistry of the cosmos carries a latent capacity for life. Billions of years ago, a barren rock organized itself so deeply that it eventually grew a mind and learned to look back and wonder how it all began.